Welcome my students and viewers as well. Till last class, I dealt with linear programming in quite detail. Initially by graphical method, then I switched over to the simplex technique, and while explaining simplex, I have explained simplex for maximization. Later on we shall see simplex for minimization. But today's class is devoted to the concept of duality, what duality means in linear programming. So today we are going to discuss this duality, right? Dual. What is dual? Any tangible object, if placed under the sun, has its shadow, it is its dual. Secondly, when any tangible object, including yourself, human, when we stand before a mirror, whatever we see inside the mirror is our dual. This is what dual concept is. Now, in linear programming, any initial problem when we come across with any initial problem of linear programming, that initial or first problem is known as the primal problem, and every primal problem has its own counterpart, and that counterpart of any initial primal problem is called dual of the primal. So this is what the basic concept regarding primal and dual. We can define dual. With every LP problem, there exists another LP problem called its dual. Right now I have told it. The given initial problem is called primal if the primal is maximization problem, then the dual is a minimization problem. Just conversely, similarly, if the primal is minimization problem, the dual is a maximization problem. So this is the very inner concept of duality. Now, how we convert any given primal into dual? So in a standard form, suppose we start from any maximization problem, this is primal. Now in the standard form it is given this maximization z, maximize z has n variables in m equations. We have m equations in n variables. Now since it is a maximization problem, definitely here the variables number is n and number of equations is m. It will exactly get converted just in a reverse way. Here number of variables would be m and number of equations would be n. So we shall see. So these are the m constraints in n variable. This is first row, so a11 x1, a12 x2, first row, first letter 1 stands for the first row, a11 x1, a12, a1 n, xn. We have n variables in m equations. This is a21 x1 plus a22 x2, a2n xn less than b1 b2. And similarly, this equation shows, finally, this is am1 x1. This is mth equation. am1 x1 plus am2 x2, amn xn less than or equal to bn. This is a standard primal problem of maximization. And in this problem, we have n variables in m equations. Now come to the dual. Its dual, since it is a maximization problem, just we have told our dual would be a minimization problem. Z was any quantity to be maximized, so definitely there would be any another quantity which would be minimized. Say this is pi. Pi may stand for cost or anything. Pi. Now see how this primal has been manipulated in the dual. All these constant, not constraint. With each constraint we did have b1, b2, bn, these all constants, these will go into the objective function of the primal dual. So b1, b2, bn, here we have it is bm. In just this problem primal, we had the decision variables as x1, x2, xm. Definitely for minimizing pi we shall need some another variables. Let it be y1, y2, ym. So now this coefficient matrix has been transposed. This first row has become first column, second row has become second column, and finally we have a 1n y1 plus a 2n y2 mn ym cn. Now we must see that here we have n equations and the number of variables are m. It is apparent right here. So in a standard way we can show any primal in a dual in this way. Now let us take a numerical example and then I'm going to show that how it is being converted. Yes, this is our primal problem and it relates to the maximization. So maximize z 20x1 plus 30x2 plus 50x3 under two constraints, 2x1 plus 3x2 plus 5x3 less than or equal to 10 and 5x1 plus 0x2 plus 6x3 less than or equal to 15. All variables are positive. Now to get its dual, first of all we must arrange this this problem, that is this one our. So this primal needs to be arranged in matrix form initially, then it becomes absolutely comfortable to get it converted into a dual. So let us arrange it in a matrix form. So 20, 30, 50, this is the row vector, these are the three variables. So we have three variables and 2, 3, 5, 5, 0, 6. This becomes our coefficient matrix and we have three variables and less than 10 and 15. Just before going to dual, we must see in this primal problem that here we have three variables. So number of variables is 3 and number of equations is 2. Exactly it will get converted into reverse way. There in a dual, number of variable would become 2 and number of equations would become 3. Let us see how it happens. Now to get the dual, it was maximization. So here we have minimization. Z was to be maximized, some another quantity is to be minimized. Now from the primal problem, this column vector is taken into objective function of dual, taking its transpose. So this is column vector, here it has become row vector, and since there are two elements in this row vector, so we shall need two variables. Now we have opted variables y1 and y2. In the primal it was x1 and x2, so this is y1 and y2. So minimize pi 10 and 15, this goes into the objective function in transpose way, y1 y2, subject to we take transpose of this matrix. Its order was 2 into 3. And when we take transpose, its order becomes 3 into 2, 3 by 2. So it is being transposed. Number of variables have been already selected, and since minimization, it becomes greater than. Now this 20, 30, 50, this was in the row vector of objective function. This has come in the constraint in a transposed way. It was row vector, here it has become column vector. Now the entire this problem could be expressed in equation form. So dual in equations, minimize pi 10y1 plus 15y2 subject to 2y1 plus 5y2 greater than or equal to 20, 3y1 plus 0y2 greater than or equal to 30, and 5y1 plus 6y2 is greater than or equal to 50, y1, y2 non-negative. So now it is primal, it is dual. We can see the symmetry. In the primal we had three variables, in the dual we had three equations. In the primal we had two equations, in the dual it has become two variables. So this is how any primal is being changed or being converted into dual. Now let us see what are the symmetry between primal and dual. I am going to explain right now. Just now we have explained how we convert a primal into dual. We have seen a numerical example. Now Finally, we must see some kind of symmetry between primal and dual. This symmetry between primal and dual is being explained under these 8 points. Number 1 says, if the primal is a maximization problem, the dual is a minimization problem. Fine. Number 2, if all constraints in the primal involves less than, then dual becomes greater than. In the primal, if it is greater than, in dual becomes it is less than. So if all constraints in the primal involves these signs, then all constraints in the dual involve just in the reverse way, this becomes. Number 3, the coefficients in the dual objective function, we have seen in the last example that coefficients in the dual objective functions are the constant terms in the primal constraints and vice versa. Number 4, the number of structural variables in the dual problem is the number of constraints in the primal and vice versa, that I have explained. Number 5, dual of the dual is primal itself. Yes, if you get a dual of the primal and if you again get the dual of the dual, you will reach at the primal itself. Number 6, the variables in the dual problem are different from the variables in the primal. There we had the terms x1, x2. In dual we took y1, y2. Now 7th point says, the coefficient matrix of the left side of the dual's constraint. The coefficient matrix of the left side of the dual's constraint is the transpose of the coefficient matrix of the left side of the primal's constraint. Very clear. I have done it mathematically, numerically in the previous. And finally, this says that the optimal solution of the primal and dual are identical. This is very important theorem, that maximum z becomes minimum pi. If you start from a primal, you get the solution, let maximum z becomes 50. You get its dual, solve it, you will get minimum pi as 50. So the very optimal solution of the primal and dual are identical or the same. So this is what about the duality in linear programming. I started linear programming right from the OR standard. I explained OR, how OR it came into existence. Then I came in this linear programming. On linear programming, initially we solved all the maximization and minimization problem with the help of the graphs. And the simplex technique I have explained for maximization problem. For the time being, I have explained this maximization problem. Then I have explained duality in today's class. This is the symmetry between primal and dual. And for now, I'll switch over from this chapter to some another chapter of microeconomics, or some probably in the next class I'll be explaining deadweight loss of the monopoly problem. Now in LP, till here any problem arises to the students or to the viewers, they must ask me in the comments. I'll be available for that. And from next class, we shall be going into some another chapter of microeconomics, that is a deadweight loss. And so this is what for today's class. One thing more, that if any student or the viewers want minimization problem by dual, then they must ask me. And if any problem of linear programming beholds with you people, you do ask me in the comments. Or minimization problem, if it becomes very utter essential for you people, then you do ask me. I will explain in the class and whenever it comes. So this is what for today. Thanks.